Salam, peace be upon you. My name is Muhammad Laiq Siddiqui, the father of Holophase. Part 32 Simulation Rules Using Computers as Practice Universes. Remember the language we are learning. There is one field, phi, the holophase, one continuous cyclic movement from which all of reality unfolds. When phi begins to change, its first derivatives appear, and with them, the three dimensions show themselves at once. Time as omega, space as k, and motion as v, built from both. Every higher derivative is a finer question about how phi changes, and each one casts three shadows together: a time shadow, a space shadow, and a motion shadow. These echoes mix and weave into one another, forming the patterns we call fields, particles, bodies, thoughts, and worlds. In this picture, everything that exists is a living tapestry of phi, endlessly echoing through its derivatives and their dimensional shadows. Today, we listen to just one of those echoes. We are climbing further into validation and testing of Episode 9, the generative grammar. In our last part, we learned the sacred rule of science: turn grammar into specific, falsifiable predictions for the lab. We became bridge builders, stress testing our blueprint. But there is a problem. Some bridges are too expensive or too dangerous to build on a whim. Some experiments are too difficult, too slow, or too extreme to perform in a lab. You wouldn't build a full-scale skyscraper to test a new architectural idea. You would build a scale model, put it in a wind tunnel, and simulate earthquakes. Today, we learn to do exactly that for the Holophase universe. We enter Part 32, Simulation Rules, using computers as practice universes. This is where our grammatical framework meets its most powerful ally and most ruthless critic, the digital computer. A computer is not just a calculator. It is a universal simulator. It can take the equations of the phi-grammar, discretize them, and step them forward in time, creating a virtual reality governed by those very rules. This virtual reality is our practice universe. It is a sandbox, a wind tunnel, a flight simulator for cosmic ideas. Our anchor image is a vast celestial orrery, a mechanical model of the solar system, but built inside a supercomputer. Picture an ancient astronomer's beautiful clockwork model of planets orbiting the sun. Now imagine that model scaled up infinitely, with not just planets, but every atom, every field fluctuation, every thought, represented not by brass gears, but by bits of information, evolving according to the precise mathematical rules derived from phi. The supercomputer's fans hum like a cosmic wind. Lights blink like distant stars. Inside its memory, virtual galaxies collide, virtual chemicals react, virtual civilizations might even arise. This is our practice universe. Today, we learn the rules for building these orreries, and we discover that by studying them, we can probe the grammar in ways no physical experiment ever could. Here is the pragmatic puzzle of this part. We have a set of equations, the phi-grammar. They're often nonlinear, complex, and analytically unsolvable for interesting cases. We can't just solve them with pen and paper to see what happens. So how do we explore the consequences of our grammar, especially in regimes that are experimentally inaccessible, like the first moments of the Big Bang, or too complex to track, like turbulent fluids? And how can we be sure our computer simulations are truly testing the grammar and not some artifact of the simulation itself? The answer is the sophisticated craft of scientific computation. It involves three key steps: discretization, integration, and validation. First, discretization. The phi field is continuous, defined at every point in space and time. A computer, however, deals with discrete numbers, so we must create a computational grid. We divide space into a lattice of points, like a 3D chessboard. We divide time into a sequence of ticks. At each grid point, at each time tick, we store a number, representing the value of phi at that location and moment. This turns the smooth, infinite field into a finite, manageable dataset. The art is to choose a grid fine enough that the discrete points capture all the essential waviness and structure of the true continuous field. If the grid is too coarse, you lose the physics. It's like trying to paint the Mona Lisa using only giant pixels. Second, integration. This is the dynamical heart. We have an equation that tells us how phi changes in time, perhaps something like the time derivative of phi equals some function of its spatial derivatives. At time tick t, we know phi on all grid points. Using the discretized version of our equation, we compute a small change in phi. We then add this change to get the new phi at time tick t plus delta t. We repeat this step by step, marching the virtual field forward in time. This is the simulation's clockwork. Algorithms with names like Rungekuta or Leapfrog are the precise gears that perform this integration accurately and stably. Third, and most crucial, validation. We must ensure that the virtual universe in the computer is a faithful puppet of the grammatical rules, not a runaway puppet with a mind of its own. We do this through convergence tests and symmetry checks. A convergence test means running the same simulation with finer and finer grids, smaller pixels, smaller time steps. If the grammar is being simulated correctly, the results should converge. They should get closer and closer to a single definitive answer as the grid refines. If they don't, the simulation is unstable or wrong. A symmetry check means verifying that conserved quantities in the grammar, like total energy tally, are indeed approximately conserved in the simulation, not drifting due to numerical errors. So here is the point. A well-crafted simulation is not a video game. It is a rigorous, numerical experiment conducted inside the grammatical framework. It lets us ask what-if questions of reality itself in a controlled, repeatable, and inspectable way. Let's explore the tri-unity of simulation. The time echo of simulation, accelerated and rewindable history. In a simulation, we have mastery over time. We can run 1 billion years of cosmic evolution in a day. We can pause, rewind, and step frame by frame through a chemical reaction that takes femtoseconds in real life. We can run the same simulation 1,000 times with different random seeds to build up statistics. The time echo is temporal plasticity. Simulation time is a slave to our inquiry, allowing us to dissect causality and explore probabilities in a way real-time experiments never could. The space echo of simulation, omniscient vision. In a simulation, we have perfect information. We can see the value of phi at every grid point, inside a star, within an atom, behind an event horizon. There are no hidden variables. We can make plots of any quantity, trace any word line, calculate any correlation function. The space echo is panoptic transparency. The entire practice universe is an open book, allowing us to see the direct consequences of the grammatical rules playing out in perfect detail, free from the limitations of our instruments. The motion echo of simulation, isolating and combining effects. In a simulation, we have control over ingredients. We can turn off gravity to see how a galaxy would evolve with just gas dynamics. We can simulate a world with a slightly different value of a fundamental constant. We can introduce a single perfect defect and watch how it moves, or stir the phi field in a specific pattern and watch turbulence develop. The motion echo is causal dissection. We can isolate individual verbs from the grammatical sentence and see what story they tell alone, then combine them to see their interplay. Now let's locate this powerful tool on the master tree. We are on the computational validation branch within book 9.8, Validation and Testing. This branch depends on the dynamical grammar to have equations to simulate, and on the computational generation ideas from book 9.5. It enables us to probe the grammar in extreme, complex, or pristine regimes that complement physical experiments. It is our wind tunnel, our particle accelerator for ideas, where we can crash concepts together at will to see what emerges. To see the power of simulation across scales, let's light lanterns from iconic computational experiments. A near lantern from engineering and entertainment. The physics engine in a video game or CGI movie. When an animated character jumps, their cape flows in the wind. When a car crashes in a game, debris scatters realistically. This is governed by a real-time simulation of simplified physics grammar, Newton's laws, simplified fluid dynamics, collision detection. The game developers discretize the world into polygons and particles, integrate the equations of motion, and render the result. They constantly validate. Does the character's jump look right? Does the debris behave plausibly? This simulation is a practice universe for visual storytelling, and its validation is the audience's belief. If the simulation is wrong, a character floats unnaturally, the illusion breaks. A middle lantern from climate science. Global circulation models, GCMs. These are among the most complex simulations on Earth. They discretize the atmosphere and oceans into a 3D grid spanning the globe. At each grid cell, they solve equations for fluid dynamics, heat transfer, radiation, and chemistry. A sophisticated, effective grammar for the climate system. They integrate forward for decades or centuries of simulated time. Their predictions, global temperature rise, precipitation patterns, hurricane frequency, are crucial for policy. Validation comes from hindcasting, running the simulation from 1850 to the present and seeing if it reproduces the known historical climate record. If it can't get the past right, we don't trust its future. A far lantern from Lattice Quantum Chromodynamics, LQCD. This is a direct simulation of a fundamental phi-grammar, the theory of the strong force, QCD, which describes quarks and gluons. Here, phi is the gluon field. Space and time are discretized into a four-dimensional hyperlattice. Using Monte Carlo integration techniques, a way to handle the quantum sum over histories, physicists compute the evolution of the field. From these simulations, they predict the mass of the proton from first principles. Think about that. A subatomic particle's mass emerging from a numerical simulation of fields on a lattice. They also predict the transition temperature at which nuclear matter melts into a quark-gluon plasma, a state that existed microseconds after the Big Bang and is recreated in heavy ion colliders. The simulation is a practice universe for the primordial fireball. From game graphics to global warming to the birth of matter, a unifying principle. When you cannot experiment directly, or when you need to see the unseeable, you build a practice universe inside the computer. Its faithfulness to reality is measured by its ability to reproduce known benchmarks and make novel, testable predictions. What then is the specific language role of a simulation? It is the grammar's own executable implementation. It is the compiler for the Holophase language. If the grammar is the set of production rules, like a programming language's syntax, then a validated simulation is the working interpreter or compiler that takes an initial condition, a program, and runs it, producing the output, the story. It answers the question, given this starting sentence, what is the full story that the grammar produces? The core question this part asks about phi is, how do we translate the continuous equations of the phi grammar into a faithful, stable, and convergent discrete algorithm? And what novel phenomena or quantitative predictions can we discover by executing this algorithm on computers? We are moving from having a grammatical rulebook to having a machine that can run the rulebook and show us the movies it produces. What does simulation do for our understanding? It discovers new phenomena and phases of matter that were not obvious from the equations alone. It calculates quantities that are analytically intractable, like proton masses, critical exponents. It explores extreme conditions, early universe, neutron star interiors. It provides synthetic data to test analysis methods and inspire new experiments. Now, stability and breakdown. Numerical simulation is a mature, indispensable pillar of science. It holds as long as the discretization is faithful, the integration is accurate, and the computational resources are sufficient. It breaks down when the system has multiple, vastly different scales that are too expensive to resolve simultaneously, like simulating every molecule in a liter of water, or when the underlying physics involves exotic phenomena not yet captured in the discretized equations, like quantum gravity effects at the Planck scale. Simulations also face the validation paradox. You need real-world data to validate them, but you often build them to predict where you have no data. This brings us to the critical synthesis of Book 9.8, linking simulation to experiment. The central claim. For any well-defined physical system, a simulation based directly on the postulated fundamental phi grammar, or a robustly derived effective theory from it, should, when its parameters are matched to the system's measurable properties, generate synthetic data that is statistically indistinguishable from data collected in real experiments on that system. The simulation should not require tuning of extra, unmotivated parameters to force a match. A concrete multi-scale measurement scene, simulating Rayleigh-Bénard convection. This is a classic fluid dynamics experiment. A shallow layer of fluid is heated from below. When the temperature difference, delta T, exceeds a critical value, orderly rolling convection cells appear, like a honeycomb pattern. At higher delta T, the flow becomes chaotic and turbulent. 1. The real experiment. We use a precise cell, a transparent fluid, and lasers to measure the velocity field at many points. We measure the Nusselt number, a dimensionless measure of heat transport, as a function of delta T, and we analyze the spatial and temporal patterns of the flow. 2. The phi-based simulation. We modeled the fluid using the Boussinesq equations, an effective theory for fluid flow with buoyancy, derivable in principle from coarse-grained molecular phi dynamics. We discretized these equations on a 3D grid. We set parameters: fluid viscosity, thermal diffusivity, expansion coefficient, all measurable. We imposed the experimental boundary conditions: hot bottom, cold top, insulating sides. We integrate the equations forward in simulated time. The pass condition, validation. The simulated flow spontaneously forms convection rolls at the correct critical delta T. The computed Nusselt number, as a function of delta T, matches the experimental measurements within error bars. The simulated velocity fields, when analyzed, show the same statistical properties, spectra, correlation lengths, as the measured ones. The simulation might even predict subtle secondary instabilities or transition sequences that can then be sought and confirmed in new, more precise experiments. This confirms that the effective phi-grammar, the Navier-Stokes-Boussinesq equations, is being faithfully executed and captures the reality of convective turbulence. The fail condition: falsification of the model or simulation. The simulation fails to produce convection at any delta T, or produces it at a wildly wrong temperature difference. The heat transport is off by a factor of 2. More subtly, the pattern of turbulence is qualitatively wrong. Maybe it's too smooth or too intermittent. If, after exhaustive checks of numerical accuracy, convergence tests, and remeasurement of input parameters, the mismatch persists, it means one of two things. Either the effective phi-grammar, the Boussinesq equations, is an inadequate model for this particular fluid system, perhaps important physics like non-Newtonian viscosity is missing, or our discretization integration scheme has a fundamental flaw that corrupts the grammar's output. Both are serious failures that force a revision, either of our physical understanding or of our computational methods. This falsifiability loop, experiment informs simulation, simulation predicts, experiment tests, is the dynamic core of modern computational physics. Let's cultivate a practical recognition skill. You can train your mind to recognize simulation thinking in any situation where a model is run forward to generate specific outcomes for the purpose of testing, prediction, or understanding. Watch a city planner using traffic simulation software. They input the road network, traffic light timings, and expected vehicle flows, the initial condition and rules. They run the simulation for the morning rush hour. It generates predictions for congestion points and average travel times, the output. They validate by comparing to real traffic camera data. They then test interventions. What if we change this light to green longer? The simulation is a practice universe for urban flow. Observe a pharmaceutical company simulating drug-protein binding. They have a 3D atomic model of a protein, a complex molecular phi pattern. They simulate the dynamics of a candidate drug molecule near its active site, calculating binding energies and kinetics. This in silicon experiment screens thousands of molecules before synthesizing a single one in the lab. The simulation's prediction of strong binder is then tested with a real biochemical assay. Consider a chess engine like Stockfish. It embodies the grammatical rules of chess. Given a board position, initial condition, it simulates millions of possible future move sequences. It runs the grammar forward, evaluates the resulting positions, and chooses the best move. Its validation is its victory over human champions. You are watching a pure grammar, chess rules, being executed at superhuman speed to explore a branching universe of possibilities. Whenever you see a model being executed to generate specific testable scenarios, you are seeing simulation. You are seeing a practice universe in action. We must connect this computational power directly to our Holophase journey. In the previous part, we stressed the need for experimental tests. Here, we see that simulations are the experimental tests we run inside the grammar itself. They are the ultimate expression of the computational generation we saw in Book 9.5. The universe is a computer. We are now building smaller, simpler computers inside it to mimic its own rules, creating a hall of mirrors that deepens our understanding. We haven't replaced reality with a simulation. We have built a looking glass through which to view the grammar more clearly. If you want to see the full mathematical derivations and exact equations behind this idea, the discretization schemes for field equations, the stability criteria for integrators, the statistical methods for analyzing simulation output, you can search for Holophase on Zenodo. There you will find the scientific papers that this audio journey is built on. Let us pause and appreciate the position in Book 9.8. We now have a complete validation toolkit. experimental predictions to test the grammar in the real world, and simulation rules to test and explore the grammar in the virtual world. This dual approach makes our framework robust, flexible, and deeply empirical. In the next part, we will look at the final, honest step in validation: failure modes and boundaries. We will preemptively ask, where do we expect the current holophase grammar to break down? What are the edges of our map? This is not an admission of defeat, but the mark of a mature science that knows its own limits. Before we end, the mandatory zoom out to hold our scope. Simulations are patterns of bits in a computer, which are physical patterns in silicon, which are, in the holophase view, high-level patterns in the phi field. We are using one complex phi pattern, a computer, to simulate other, simpler or more focused phi patterns. It is the universe, through us, simulating aspects of itself. We have added no new substances. One field, phi, plus its infinite tower of derivative questions, plus the ingenuity to encode some of those relationships into algorithms that run on phi patterns called computers. From this, we gain practice universes, proving grounds for our comprehension. As we conclude, hold the image of the celestial orrery inside the supercomputer. Its gears are algorithms. Its clockwork is integration steps. Its planets are data structures. But the laws that make them move are the very grammatical rules we have been climbing the master tree to learn. By building and studying this orrery, we are not playing God. We are being diligent students. We are running the equations ahead of time, in a safe space, to see if they produce a cosmos that looks like our own. If they do, our grammar gains strength. If they don't, we have found a crack in the foundation, and the real work of understanding begins anew. The simulation is our practice universe, and in it, we practice reading the mind of God. Salam, and peace be upon you.